Today's presentation is entitled Understanding the Evolution of Metallurgical Flow Sheets in a Holistic Manner, a zinc sulphate case study. I am very pleased to introduce our presenter, Nicole Uys. Nicole Uys is a PhD candidate within the Minerals to Metals Institute at the University of Cape Town. She is in her third year of her PhD entitled Developing a Process Mineralogical. As you can see, I'm absolutely petrified by any scientific phrasing. I just, for some reason, completely need to Google search how to pronounce it properly beforehand. So, Nicole, this will happen throughout your presentation. If I have to read out questions, I might just freeze up. Anyways, sorry about that. Approach towards the design of variable process flow sheets, a zinc sulphate case study. And she did this under the supervision of Professor Jochen Peterson and Associate Professor Megan Becker. Nicole completed her BSc in Chemical Engineering in 2014, and did her postgraduate diploma in Management in Entrepreneurship in 2015 at UCT. Thank you so much for joining us today, Nicole. Over to you.
Thanks, Aysha. Okay, I'm going to quickly share my screen. All right, can everyone see everything? Okay, let's get going. So,
Yes, we can.
Yeah, perfect. Thanks for the introduction, Aysha. So today I will just be giving you an overview of my PhD and taking you through a section of some of my recent work. So our society's demand for metals is continuously increasing. This is obviously due to population growth, increased urbanization, amongst many other factors. However, the metal industry is currently facing a multitude of challenges. One particular technical challenge is increasing ore complexity and lower grades. And while we acknowledge that these technical challenges are compounded by volatile market conditions, increasing costs of energy, labor, waste disposal, legislation changes due to historical environmental degradation, and also obviously increasing pressure from society to reform. The sort of premise for this is that many of the processing and environmental considerations for process design can be linked back to process mineralogy. There also appears to be an absence of methodologies or approaches to holistically analyze the sustainability performance of new technologies or a combination of existing ones. So this thinking could be applied to almost any metal. However, I have chosen to place this in the context of zinc. The reason being is that it is a strategic metal, which is in danger of a supply deficit in the future. This would be very problematic for our construction industry who use the bulk of our galvanized steel. And another reason for choosing zinc is that it has a variety of significantly different processing routes, from hydrometallurgical to pyrometallurgical, and it's also associated with a multitude of other valuable and useful metals. Given that the zinc industry has historically and continues to operate at the margins, careful consideration and forward thinking are needed when designing flow sheets for facilities, for new facilities, and for the retrofitting of existing ones. Historically, zinc appears to be have been produced in isolation with a limited product basket and a lack of interplay between waste streams and technology options. However, research thus far has suggested that by diversifying the product suite, it is often crucial for the long-term economic viability of the zinc industry. So in this way, the industry can, to some extent, accommodate for market fluctuations if they've got more products that they can sell at different times. But first, let's just briefly discuss the mineralogy of zinc ores. So certain minerals and therefore metals often occur naturally together. This is a metal wheel which visually explains which metals are commonly found in association with each other. The most commonly processed zinc ores contain zinc sulphides, with the primary economic and important mineral being sphalerite. Within a deposit, zinc minerals are typically associated with lead in the form of galena and copper minerals such as chalcopyrite. This results in a co-production of these metals with zinc. Also, other co-products can include cadmium, copper, cobalt, and nickel. There are also other valuable miners such as silver and gold, which have historically been produced with zinc. And in the future, these ores also represent a significant contribution to the world's specialty metals, such as your indiums, germaniums, gallium. I could go on forever. Of course, zinc also has certain deleterious elements associated with them, such as mercury and your halides. And then you've also got some elements that, depending on your process, you could call them valuable or deleterious. Traditionally, standalone zinc refineries are not typically designed to recover a variety of metals contained within these zinc concentrates. The refineries therefore consider these as penalty elements, and they essentially charge the miner who produces the concentrate if these elements are present in certain quantities. So as you can see from this, from the metal wheel previously, that zinc isn't a single commodity. There are so many other things associated with it. And we've only been historically focusing on the zinc, lead, copper, gold, and silver as our main ones. But we're not going to get away with this going forward in the future. Processing decisions cannot be made in isolation. We need to start considering today's economics and environmental implications. So with grades falling, it's starting to diversify our product offering may be a good alternative. And refineries who can start producing these other smaller elements, such as cadmium or indium and germanium, that would otherwise be considered or that you would otherwise be fined for, can then actually benefit from discounted concentrate prices. And just remember, whatever you don't extract ends up in your waste streams. So zinc has a long processing history with a huge amount of different refining options available. So in my research, I found it very useful to display these as a timeline to understand when they came about and why. What I haven't shown is that pyrometallurgical routes have been around for hundreds of years earlier, but these ones are no longer in use today, and so I haven't shown them. So to start off, in the late 1880s was when the first commercial hydrometallurgical process was implemented. This paved the way for what is still the most widely used process route, which is called roast leach electrowinning, or RLE. During this time, the ore was still being hand sorted, and in Australia and in Canada, they developed froth flotation and differential flotation. And this was a game changer in terms of separating out the gangue from valuable minerals. And it's still used today in the industry. The successful extraction of zinc using electrolysis in the early 1990s paved the way for this dominance of the RLE process. However, the presence of the roaster, which then removes sulfur from your initial mineral, resulted in the production of zinc inextricably being linked to sulfuric acid. Now, although you might say, okay, but we spoke about earlier making as many products as possible. Yes, that's fine. And sulfuric acid does represent an additional income source. However, the market for sulfuric acid can be quite saturated and is not always in harmony for zinc. So this can actually often become a hindrance or a problematic product that you can't get rid of. So this RLE process stagnated in its adoption during the mid-1990s due to the inability to remove iron from the system. So during that time, another pyrometallurgical route came about, the imperial smelting process, which was fairly widely adopted. But then what happened in the 1960s is they solved the iron problem. They came up with a few different routes to remove iron from the system. And after that, the roast leach electrowinning process took off and still accounts for over 85% of zinc production today. However, they were getting more and more concerned that your zinc was now linked to sulfuric acid. So they started looking at ways to produce the zinc without producing acid. And these different processes are direct leaching processes, which try and prevent this acid formation. And they produce elemental sulfur instead. Depending on the impurities you've got in your system, you can then have a saleable product. These processes haven't been widely adopted throughout the industry, although they definitely, from a technical point, work, and but RLE still seems to be the favorite option. During this time, other technology developments such as the Aysha mill and the Jamison flotation cell came about, and these came about directly to address certain mineralogical concerns, and there was a need to increase the liberation of your zinc within your different minerals. So, and then somewhere during there, we have another pyrometallurgical process, which is often used to treat residues. And recently, there's been another development in terms of flotation. So as you can see, zinc has a long processing history. There are a lot of options available. And so now we're just going to talk about one or two of them in a little bit more detail. Okay. Trail and Flin Flon are two case studies that I will be talking about later. I just wanted to highlight for you when they started operating. And at that time, the only process that they could use was the RLE process. Okay. So once again, here are your different routes shown in a different format. Your green represents mineral processing, your orange is your pyro processes, and your blue are your hydro processes. And this process is what I am referring to as RLE and accounting for over 85% of zinc production. One drawback with this process is that it produces large amounts of waste, particularly from the iron precipitation steps. So different processes have different advantages and advantages and disadvantages. But all of them usually start with just before the black box, which is roasting. Most refining processes start at that place. So depending on the feed, you could start blending your different ores together to get either consistent feedstock. You could be blending your concentrates to ensure that you've got more valuable metals such as silver or indium germanium, or you could be blending to try and get rid of or dilute a deleterious element such as manganese. Quickly before we move on, the pyrometallurgical processes often have the advantage in that the waste that they produce is usually of a smaller quantity and is usually quite stable. And so there isn't that long-term environmental risk, as opposed to the hydrometallurgical routes, which are able to selectively and sequentially extract a variety of valuable minor elements which would otherwise get lost in the pyro processes. So when you're considering mineralogy, it's more important for your hydrometallurgical steps. But anyway, there's a whole multitude of routes to choose from, and the point is that there's no obvious route that is always favored over another. So pressure leaching is the other process that I will be talking about further. So up to now, we've only been talking about zinc processing, and as previously mentioned, it is produced in isolation. This approach can often produce large quantities of waste and doesn't necessarily maximize your value potential. If you start integrating your zinc processes with, say, lead and copper, you could suddenly start extracting a greater variety of metals from your ores. But obviously this depends on the mineralogy. So when I just want to clarify that when I say you could be reducing your amount of waste when you interlink these different processes, it may not be necessarily decreasing the quantity, but it may be reducing its toxicity. And also waste could also be viewed as thermal, so energy. So now that we've discussed the mineralogy and we've looked at the different process routes, let's talk about 2 zinc operations to understand some of the historical drivers of this technology route choices. So I looked at historical case studies that covered a variety of different processing routes. I will just be discussing 2 of them today, Trail and Flin Flon. Both of them are in Canada. I had the opportunity last year in October to visit both of these plants, so that's why we'll be talking about them. Most of these operations have been around for over 100 years, and they're also regarded as pioneers within their field. So let's start with Trail. It's based in British Columbia. It's an integrated zinc and lead refining facility, and it produces an absolutely huge range of processing of different products, from your metals to sulfur products. I'll be here forever if I list all of them. It is interesting to note that the power for this process or for this facility is from a hydroelectric dam. You can see it in the picture there on the left. That Trail built themselves, and up until recently they owned entirely. So this source of energy is quite important for facilities going forward. And then the little red dot that's just appeared is where they're now sourcing their ore from. So right up in Alaska, whereas they originally were processing it quite close to the refinery. So let's do a timeline also for Trail. Trail was originally processing gold and also copper ore from the nearby Roslyn mines, and then they started with lead in 1902. This changed with the advent of World War I. Suddenly there was a demand for zinc. So in response, they had zinc in their ores, so they started actually refining it as well. So for most of the 20th century, the Sullivan mine was the main supplier. It was rich in your lead, silver, and zinc, but it was unprofitable because of the difficulties in separating this complex combination of minerals. Because remember, they were hand sorting it. So they'd managed to discover and develop differential flotation. And as I said before, this is used all over the place in all the different metal industries and was an absolute game changer. So they were suddenly able to produce zinc. The problem was then they started increasing their SO2 emissions. And so from an environmental perspective, they started producing sulfuric acid, which they made into fertilizer in the 1930s to address this environmental issue. However, unfortunately for them, this was right when the Great Depression hit and affected their market for fertilizer. As part of their modernization program in the 1970s, Trail wanted to increase zinc capacity again, but now they didn't want to increase, their environmental emissions, and they didn't want to increase their sulfuric acid production. Because remember, we said with roast leach electrowinning, the more zinc you produce, the more acid you produce. And so they wanted to produce more zinc, they didn't want the acid. So in order to achieve this, in about 1980, 1981, Trail introduced the first commercial pressure leaching operation. It's just a single stage, low acid system, and it was integrated in parallel. So both the existing system was running and they added the smaller system. I think it added about a 25% capacity to the system. So now they increased their zinc production. The problem is they increased their residue as well, so their waste. What they then tried to do is introduce a QSL lead slag fuming process to process the stockpiled residue and also to process their lead concentrates. However, this process was unable to accommodate these high residue amounts, and so it didn't actually work, so the whole thing failed. They then went back to the drawing board and they installed a KIVSET furnace. So they just replaced it with a different type of technology, and that is still being used today. It had the advantage of decreasing their lead emissions and also recovering any of the lost zinc. In the early 2000s, specialty metals such as indium became more important in the marketplace, and so they introduced a new expansion to particularly process and recover indium and tin and all sorts of other things, and germanium. And they also at the same time tested out a pilot heap leaching system, and it was, although it was technically feasible, they couldn't get the economics to work. The same thing where they had a leftover furnace lying around, and they tried to see whether they could recycle e-scrap, so scrap metal and electronics. Same thing, it was technically possible, they just also couldn't get the economics to work. So as I said before, the majority of the 20th century they were on a mine that was a couple of 100 kilometers away from them. But in the 1990s, they knew that this was running out, so they started transitioning over to a different mine, which is based in Alaska. So now you've got a huge transportation consideration of where you're getting your concentrate from. Also, what they do is they get other concentrate from Peru and Bolivia, which is high in their silver and their specialty metals, such as indium and germanium. And in that way, they can produce more of those certain metals. So just quickly looking at the mineralogy of trail, all I really want to show you is, let me get a pointer quickly. So trail produces, essentially blends all their concentrates together. And the ones they particularly care about are your zinc and your lead. And then they supplement from the Peru and Bolivia concentrates. The key differences between Sullivan and their new ore, which is Red Dog, is in their iron. So previously they had pyrite and marmotite, and now they are dealing with pyrite and marcasite. So it's just a different form of their iron. But this actually has a huge implication for their pressure leaching technology that they use. And just quickly summarizing this again, so they started off with their roast leach electrowinning process. They added in a fertilizer plant. They added then a pressure leaching system, and of the Red Dog concentrate that they get, 50% of it is only sent to pressure leaching. So the reason for this is that the pressure leaching needs to be optimized for a very particular type of concentrate to achieve the best results. And even the annual variations from this Red Dog concentrate can cause instabilities. So from what I can see, this is one of the apparent disadvantages of a pressure leaching system, is that it requires a very dedicated feed source that doesn't vary too much. And then I showed you that they introduced their KIVSET furnace for their lead smelting. And the advantage of this is that you can start integrating the waste streams between the two of them, so that you get a less amount of waste, you get more recovery, and the waste that's produced is benign. Let's move on to Flin Flon. It's located in Manitoba on the border of the Manitoba and Saskatchewan provinces in Canada. It is a zinc and copper operation, so no more lead here. And it also has quite a high content of silver and gold, which makes it economically valuable. They used to produce copper metal, but this ceased in 2010. It is the world's first two-stage pressure leaching system. And as you can see where it's located, it's sort of in the middle of nowhere. And we'll speak about that in a second. Interestingly enough, they also are powered by a hydroelectric dam. Not sure what happened there. Okay, so a roast leach, an RLE process and a smelting operation were started in Flin Flon in the 1930s. In the late 1980s, they realized that there was environmental legislation coming into play and their current emissions were not going to meet the standard. So they needed to upgrade the zinc system, and they introduced their first two-stage pressure leaching system in the world. So it entirely replaced the previous system. So when we were speaking about trail previously, they put them in parallel and kept the old system going. Here they completely scrapped the old technology and are only now using the pressure leaching. The main reason that they did this is that they didn't want to produce sulfuric acid. They're in the middle of nowhere. They then have to transport this acid to a coast via rail, and it is way too expensive, and the market for sulfuric acid is too unpredictable. The one drawback maybe from a design aspect with Flin Flon is that although they're not producing the acid, they're then producing elemental sulfur, which could have been sold. Unfortunately, there are too many deleterious elements present, which then contaminated their sulfur. So they're only producing very select things. They're not producing a whole basket suite, such as trail is. And so they introduced their pressure leaching system there, and they ceased copper production in 2010. One, because they couldn't meet the environmental emissions and would have had to replace the entire furnace. And two, their ore grades that they had were decreasing in copper. And so it just wasn't economically viable to actually produce another smelter. Flin Flon's also been supplied by a variety of mines, but all of these are very locally surrounding the refinery. So they wouldn't economically be able to buy in concentrate. So this particular operation is completely dependent on the local mines. Okay, let's hurry up. So Flin Flon, I've told you they have a variety of mines surrounding them, and the really important thing is that they've got decent gold and silver concentrations, which makes it quite economically viable. Not shown on here is a couple of deleterious elements that cause problems, such as mercury. And quickly, so this is a simpler process than trail. They used to have a copper smelter and they had a zinc plant. Some of their mines have finished and they no longer have the copper smelter. So just to quickly summarize those two and some of the reasons behind the changes that were made are mainly due to economics, mineralogy, and environmental, usually legislation. So in terms of Flin Flon, initially, both of them chose the roast leach electrowinning process initially when they started their design, the reason being it was the best available technology, and they mainly did it from an economic perspective. The reason that trail is highlighted in red as well for the ore is that they had to develop their flotation methods to be able to process the ore. When they started changing their design, from a trail perspective, it was done based on the economics, and also there were legislation changes coming into play. Similar thing with Flin Flon, environmental legislation drove the change. And this one actually also should be highlighted in dark blue, my apologies, because they didn't upgrade their copper smelter because from it was an economic consideration. So looking at both of those, what were some of the key influential factors? Number one was location. So when you design your refinery, are you linking it to the life of mine? In the case of Flin Flon, once the mines are completely finished, you will not be able to run that refinery. The economics do not work to buy and concentrate. Trail, on the other hand, has managed to transition actually 3 or 4 times in terms of their mines. And they're also on a bigger scale than Flin Flon is. So this is something going forward that the location of a refinery can play a critical role, one in the selection of the technology and also just in the overall life that you design your process over. Another consideration is your technology choices. Both of them initially chose the only one that was available to them, but when you choose new ones, you should also be looking at technology choices and waste management everything's linked here. But your different technology choices will impact the types of waste that you produce. It's also, you will choose the technology from a cost perspective, maybe either capital or your operating ones, and also based on your mineralogy, depending on where your elements are going to end up. From a waste perspective, this also comes down to the leadership within the company, but is also driven by legislation changes. From Trail, I think, was big enough that they had the ability to invest in not quite doing things properly, but doing things the best way they could with the technology they had available to them. Flin Flon was a bit more remote, also smaller in scale, and so they opted for residual tailings type dams for long-term storage of their waste, whereas Trail added in different technologies to try and make a more benign pellet form of their waste that they can use in the construction industry. And just another consideration for energy, although I don't really talk about it too much, both processes use hydro energy, but depending on where you are in the world, that's an important consideration, as well as who owns it. Okay, I'm going to, I think, skip over this because otherwise I'm going to run out of time. But I think we've spoken about this already. The mineralogy is really important, and you can also then start considering intertwining different technologies. So we've looked at the technical, so we've looked at all these things. Now, how do we combine the technical, environmental, and economics, link this back to mineralogy, and actually do something useful with it? So now we're actually getting to my current part of my PhD. And so the emphasis here is on process modeling as underpinning everything, and then linking it, of course, to environmental impacts, the economic aspects, and then you can start changing your feed variability and to see how this impacts, one, what you can get out in terms of value, and how you can minimize the toxicity of it. Okay, this is a lot of words. I will explain this in pictures in the next slide. But the aim of my PhD is to try and to demonstrate that process design for a heterogeneous and complex ore body, taking into account all mineralogy and the viable aspects of sustainability criteria, that this will significantly influence which flow sheet options you should choose. Yeah. So breaking this down, is that you have your mineralogy. It can obviously be complex and there's different aspects to it. If you had iron, a certain type of iron, for instance, you could choose pressure leaching as long as there aren't too many deleterious elements that would contaminate your sulfur. If you have certain other deleterious ones, you might want to choose a pyrometallurgical route so that your waste, your nasty elements end up in your slag and get captured. If you've got other elements that you want to recover from an economic perspective, you may choose the more typical roast leach electrowinning and keep adding on different units to try and maximize the value that you get out of things. Process route modeling essentially offers a systematic method to analyze all these different things. So that's what I've been doing. I've chosen a program called HSC, which stands for enthalpy, entropy, heat capacity. But essentially, I can design these different flow sheet models in my process and start playing with them individually and start linking them together. I sourced my data from literature and also from the employees at my case studies and also technical reports. In case you forgot where the previous flow sheets that I showed you fit in, I've currently been doing the roast leach electrowinning process, one of the pyrometallurgical routes, and the pressure leaching. What I'm trying to do is that look at elemental deportment. So depending on where you start and the mineralogy that you feed into your system, you want to see where do these elements end up in what quantities. Do they end up as a product or do they end up as waste? And you can start doing this with flow sheet modeling. Keep in the back of your mind that it doesn't just have to be ore, you could also be recycling, for instance, the e-waste that we spoke about earlier. This can still form part of your inputs. You need to also consider not just the material flows, you should also consider energy. And one way to consider these energy inputs and outputs is through something called an exergy analysis. So exergy is essentially trying to measure the amount of usable energy before and after a process. And so it's looking at the how efficiently your process uses energy. This is just, this image is just to illustrate the type of comparisons that you can do between different flow sheet options. So if you have a certain amount of energy that you put into your system, how well or how much losses are there within the system. Just to clarify that energy or exergy analysis should not be the only parameter you look at, but just for this presentation, it's the only one that I wanted to draw your attention to. So starting to finish off, what I'm trying to do is that there's often a danger at looking at processes too generically without taking into account local conditions. And so the aim is to develop a tool that can maximize the sustainable value proposition within the zinc industry, but it also accounts for your local context, such as your mineralogy or your energy mix and any other environmental particular context that you want to consider. It also has potential for adaptation of this approach to other commodities, such as your copper cobalt systems. And so the idea is that we think that it has relevance to the sustainable development of the extractive industry in Africa. So just to thank people who have financially backed my PhD has been SAMRI, DST, and NRF, and to the research groups that I've been working with, Hydromet, Minerals to Metals, CMR, and also the employees from Flin Flon and Tech who have assisted me with the 2 case studies, and lastly, special thank you to professors from one in Canada, Professor Asselin from UBC and Professor Reuter from the Helmholtz Institute, who have also been assisting me. Thank you.
Hi, Nicole. Thank you so much for your presentation. It was incredibly well communicated. I really appreciated it. Your ability to make scientific information accessible to those that are not necessarily inclined was really fantastic. I really also appreciated the mapping process in terms of the historical development of these technologies. So thank you. I would like to hand over to Monica Cujo, who rose her hand during the discussion to come onto the panel and just, I suppose, address and ask a question if she has one. Monica, are you able to join us? There we go.
Hello.
Hi, Monica.
Thank you very much for your presentation. I just wanted to ask, what software did you use to develop your process maps?
Hi, Monica. Thank you for the question. I've been using HSC. Sorry, I realized I skipped over that quite quickly. I thought I was running out of time. So it's HSC. It was developed by Autotech.
Okay. All right. Thank you.
Thanks, Monica. So just a reminder to all to type in their questions into the Q&A section at the bottom of your screen. Otherwise, I would like to just ask you a little bit more about maybe more clarity on some of the key concepts. So, and this is definitely stemming from my keen interest, and maybe it's coming back to basics a little bit. But so mineralogy, does it usually consist of this mapping of historical developments, or is this kind of just your genius way of conveying information?
I think if you're dealing with just mineralogy, maybe not, other than mineralogy, you need to understand the history and sorry, I'm not explaining this very well. In terms of mineralogy, you've got your entire ore body, okay, and this takes time to process it, and an ore body is not homogeneous, so you'll have different pockets which have higher particular grades or variability than other ones. So for me, because I was looking at the refinery, I needed to understand how their feed had changed over the years, and I wanted to see whether this change had impacted on their choices of technologies or anything else. So that's, from my perspective, why I was looking historically, is because my focus had been on the refining aspect for that, and then trying to translate the history or the historical learnings into going into the future for new processes when they're faced with, okay, our local mine is running out and we need to source a new one. What are some of the considerations? Or when you build a brand new process up front, how do you try and design this to think that, what if my feed changes? What are the implications for that?
I think this is very necessary work in terms, and I'm very excited about it, because this kind of integrated design process looks incredible. So I have a question here from Gerard. What mineralogy methods do you recommend for this type of process modeling?
Do they want to maybe verbally expand on that?
Gerard, would you mind stepping forward onto the panel? Or you can type in, there we go. If you'd prefer to type in maybe an expansion on the Q&A section, that's also. I
mean, what I'll do is I'll explain as I'm just worried that I'm going to miss your question, but
I think. Okay.
So at the moment, what I'm still in, so what I've been doing is setting up the kind of generic flow sheets and now starting to adapt them to the case studies. So at the moment is where I'm grappling with how much information can you, of the mineralogy, can you start feeding in? Because of course, things like texture, how do you translate that into a metallurgical response in your smelter or in your leaching things? So there will be certain bits of information that are easier to use than others, but that doesn't mean that all the mineralogy is, or that information is any less important. So that is an aspect that we are still grappling with, or will be kind of the next stage that I will be grappling with. What we were initially doing was just taking the minerals and mapping them to the individual metals using essentially what the plan is to take a certain number of minerals, translate those into metals, and what I will probably start doing is that, for instance, for pyrite or peritite, those will have different metallurgical responses, and so I would have to try and tailor, but almost manually, tell the program, treat this type of iron in a certain way up to a certain point, until it gets leached, and then it just becomes an individual element. I'm not sure if that's answering your question, but at the moment I'm not using particularly necessarily QuemScan or MLA data. I'm trying to get a holistic idea of the different minerals involved, and needing to know that certain types of minerals will respond in certain ways, and I will have to manually tell my flow sheet to treat them in certain ways.
Thanks, Nicole. You have a comment here that you have an excellent presentation, and thank you. Do you consider bioleaching of the zinc concentrate as a flow sheet option?
Thank you for the question. Before I upgraded to my PhD, I spent 2 years using a program called SAIMM, and that deals with bio heap leaching. So it's a program, that an Excel and Fortran based program that one of my supervisors was part of developing, and that is specifically geared towards bioleaching. The idea was that we would be able to incorporate that particular program into the HSC system, because it still can communicate via Excel or that sort of medium. I haven't done it as of yet, but it definitely is on my radar to do. Particularly because my one case study, Trail, did it as a pilot study, and even in my 4th year, I did a small project on the heap leaching associated with Trail. So I'm definitely not ignoring it. I just focused on a few initial starting points which I presented in the presentation. But yes, definitely that is another process that I have taken cognizance of. Thank you.
Thanks, Nicole. So I have a bit of a, there's a comment here from Jurgen that says, should stress that heap is a, oh, can you see it?
Yeah, so let me get back to the SAIMM program that I was referring to was actually specifically calibrated and designed for Trail's pilot heap leaching system. So a lot of work has actually already been done, particularly for that one case study, in applying heap leaching to that one.
And then he just reiterates that this was a bio leach. I think. So maybe another back to basics question from me, if you're willing. But because of course I'm coming from at least my thesis dealing with e-waste in the more regulatory sense and kind of looking at the social economic issue around e-waste, but what are deleterious, am I saying that right, elements? And I'm assuming that some of these will find their way, and I'm guessing that that's where mercury sits, but I would just maybe like a little explanation as to what that means.
So deleterious elements are really just ones that we flag that are problematic or we don't like or cause problems, so hence the name. So like I said, certain ones just universally we just don't like, and then there will be certain elements that, depending on which process route you've chosen, that you can or can't deal with. So for instance, if you've got all your halides or your fluorine, chlorine, if you put that in a roaster, they will fume off, and then you can capture them and recover them. But if you put them in a pressure leaching system, they might end up in your sulfur product and then contaminate it. Other things that are usually considered are, of course, yes, the mercury, arsenic, antimony are the ones that could kind of go either way depending on your particular process. I've got, I think, 2 questions that came to me directly. I'm not sure if you can see them.
Yeah, from Tekani and Waldemar.
Yeah. Okay. Should I answer those ones just directly here?
Yes, if you could integrate the question into your answer, that would be great for the recording as well.
Okay, so in response to where in the flow sheet do you feed recycled material, if considered, and what type of recycled material? Okay, so that depends on the process that you've particularly chosen. For instance, in the pyrometallurgical routes, they often put in your dusts that you start collecting. So when you do your drossing, and also I think in your steel industry, there's quite a lot of dusts or galvanizing process. There's dust that are created. You can feed that back into a smelter, for instance, quite easily. So those would be probably the ones I would consider within my project. But there's no reason why anything like electronic waste couldn't also be thrown into a furnace with other primary minerals or concentrates. And then in terms of the other question, for the different flow sheet options, what approach do you allow for capital cost estimation, factorization from previous cost estimates? Okay, so also this is another aspect that I will be grappling with following on that I've now got my basic generic technical flow sheets. Now I can start adding to it, one with the environmental and the economics. HSC has a built-in costing function, but I need to explore it to see what the limitations of it are, and then I may have to then do separate analysis for the costing for those different processes.
Thank you, Nicole. And if there aren't other questions coming through in the next 2 minutes, I'd like to just extend a call to all the participants here. If they have research that they want to present on this forum, please do reach out to me. My name is Aysha, and I'll send my email in through the chat. But if you have something that you would like to share, and this would be a good platform for you, please do reach out. And also heed the structure that Nicole has presented in quite a accessible manner. This ability to juggle the more technical aspects and put it into a context that, you know, we can all kind of follow the map together. So yeah, I'd like to then also just thank Nicole so much for her presentation. I will be sharing quite a lump of recordings and presentations towards the end of the year with all of the presentations and recordings together. So that is quite exciting and yet to come. We do have one more question. Sorry, I didn't see that in the chat there. To check robustness of process step, as in what lab tests, pilots, or analogy benchmarks are there? I'm going to just hand that over to you, Nicole, quickly for last 2-minute answer.
So I have not been doing any lab work personally, just in this kind of it was taking a higher view than going right down to the lab scale. In terms of where I'm sourcing the information, it's mainly from plants that are running. So with Trail and Flin Flon, it's from the full plant-wide scale. But for instance, with a heap leaching operation, there isn't a commercial zinc one. Well, okay, I sort of stand under correction. There's a sort of combination one, Televara. I'm not going to pronounce it correctly, but the one I will be using there for the information is from a pilot scale one. Once you have the generic sort of flow sheet, you could then, of course, apply it to a pilot or a full-scale plant. But I'm not going through the rigorousness of comparing it to lab scale, to pilot, to full scale in that way. I'm trying to compare it or calibrate my models as directly as possible to full scale plants. So the idea would be that we looked at historical ones, and then ideally with and identifying one that is then in progress to actually see whether the application is valid or not.
Thank you so much, Nicole. I think we've had a very fruitful discussion, and I'm going to now close the session. Again, please do send me an email if you'd like to be added to the mailing list or would be interested in presenting on this forum. Thank you so much, everyone, for attending, and I'll see you next week.